talking about rocket, okay? Rocket. What is rocket? How to work the rocket, and what is the principle of rocket, okay? And rocket is a device. Rocket is a device which is used to take satellite. Rocket is a device which is used to take a satellite at the desired height as well as to placed into the orbit. Okay? Desired height. Rocket is a device which is used to take a satellite, to a desired height as well as to place it into an orbit. Okay? Principle. Rocket propulsion is based on the principle of conservation of momentum. Okay? Momentum. Okay? Rocket propulsion is based on the principle of conservation of momentum. Or rocket carries both the fuel. A rocket carries both the fuel like a liquid hydrogen or liquid paraffin. Liquid hydrogen or liquid paraffin. Okay? Liquid paraffin. Rocket carries both the fuel like liquid hydrogen or liquid paraffin and a suitable oxidizer like oxygen, hydrogen peroxide or nitric acid, okay, which burn in combustion chamber within the rocket. The large burnt up gases like carbon monoxide, steam, etc., rushing out through an orifice at the back or tail end of the rocket. In consequence, the rocket is propelled forward Newton's third law of motion. Okay? This is because the momentum lost by the jet of fuel gases must be equal to the momentum gained by the rocket. Okay? Single and multi-stage rocket. In order to escape the rocket from the Earth's gravitational field, it must attain an escape velocity 11.2 km per second. 11.2 km per second is a escape velocity. Okay? Our orbiting velocities 8 km per second. 8 km per second. This is the orbiting velocity. Okay? To be able to orbit around the Earth close to its surface. To achieve this, the mass ratio m0 upon m must be 270 or slightly more than. Hence, m is the initial mass of rocket and capital M, and m is the that after time t. In either cases, the rocket has no encounter and overcome the resistance of air. This means that a little more than 270 kg of the fuel will be consumed for every 1 kg loss of mass of the rocket in terms of burnt fuel. Even today, no single stage rocket is capable of such a performance. Therefore, we have to use a multi-stage 2, 3 or even more stage rocket to achieve the desired requirement. Okay? In a multi-stage rocket, when the first stage is ignited takes the satellites to some height. When the fuel is completely burnt up, when the job of first stage is over, it gets detached and is discarded. Okay? Immediately the second stage takes over the task of producing further acceleration. The second stage gets detached and the third stage takes over the further job and so on. Okay? The velocity of the rocket thus goes on increasing at each stage and stage, and finally horizontal thrust puts the satellite in an orbit around the earth and reaching to the desired height. Okay, here to derive the relation for propulsion, let us suppose that rocket along with its fuel has mass capital M and is moving with velocity capital vector V at any instant. Let this velocity be considered with the aspect to some inertial frame. Okay, and we will be talking about rocket in initial. Okay, thank you. Rocket is a device. Rocket is a device which is used to take a satellite at the desired height, desired height, as well as to place it into an orbit. Okay, into an orbit. Okay, principle. Rocket propulsion is based on the principle rocket propulsion is based on the principle of conservation of momentum, A rocket carries both the fuel. Both the fuel, like liquid hydrogen, like liquid hydrogen, or liquid paraffin. And a suitable oxidizer like oxygen hydrogen peroxide or nitric acid, okay, nitric acid, which burn in combustion chamber, which burn in combustion chamber, within the rocket, okay, within the rocket, within the rocket. Okay, the large quantity of heat, the large quantity of heat of combustion produced greatly raises pressure inside the chamber resulting the burn of gases like carbon monoxide, steam, etc. Rushing out through an orifice at the back are tail end. At the back are tail end. Okay? At the back are tail end. Okay? Of the rocket. Okay? In consequence, the rocket is propelled forward. Newton's third law of motion. Forward. Newton's third law of motion. Newton's third law of motion. Okay. So first, Newton's third law of motion. Okay. This is because the some momentum. This is because the momentum lost by the jet of fuel gases must be equal to the momentum gained by the rocket. Momentum gained by the rocket. Okay, by the rocket. Okay. Rocket is a device which is used to take a satellite at the desired height as well as to place it into an orbit. Okay, principle. Rocket propulsion is based on the principle of conservation of momentum. It's important. Okay. Rocket propulsion is based on the principle of conservation of momentum, or rocket carries both the fuel like liquid hydrogen or liquid paraffin and a suitable oxidizer like oxygen or hydrogen peroxide or nitric acid, which burn in combustion chamber within the rocket. The large quantity of heat of combustion produced greatly rises pressure inside the chamber. Okay? The large quantity of heat of combustion produced greatly rises pressure inside the chamber, resulting the burn of gases like carbon monoxide, steam. It is rushing out through an orifice at the back or tail end of the rocket. In consequence, the rocket is propelled forward Newton's third law of motion. This is because the momentum lost by the jet of fuel gases must be equal to the momentum gained by the rocket. Single and multi-stage rocket. Single and multi-stage rocket. Okay. Single and multi-stage rocket. 1 minute. Single and multi-stage rocket. Single and multi-stage rocket. Okay. In order to escape the rocket from the earth, gravitational field Earth's gravitational field, it must attain an escape velocity. It must attain an escape velocity. 11.2 km per second. 11.2 km per second are orbiting velocity. Orbiting velocity 8 km per second. 8 km per second. To be able to orbit around the earth close to its surface. Close to its surface. Okay. Surface. To achieve the mass ratio. To achieve this the mass ratio capital M naught by capital M mass ratio capital M naught by capital M must be 270 or slightly more hence here M naught is the initial mass of rocket. Initial mass of rocket. Okay. Initial mass of rocket and capital M that after time t, and capital M that after time t, okay. In either cases the rocket the rocket has to encounter and overcome the resistance, okay, overcome the resistance of air, okay. This means that a little more than little more than 270 kg, okay. 270 kg of the fuel will be consumed for every 270 kg of the fuel 270 kg of the fuel will be consumed for every 1 kg. Will be consumed for every 1 kg. Every 1 kg loss of mass of the rocket, in terms of burnt fuel. In terms of burnt fuel, okay. Even today no single stage rocket is capable of such a performance, okay. Therefore we have to use multi-stage today. No single stage rocket is capable. No single stage rocket is capable of such a performance, Therefore we have to use multi-stage today. Therefore we have to use multi-stage 2-3 are even more stage rocket to achieve the desired requirement, to achieve the desired requirement, desired requirement. Okay, in a multi-stage rocket, in multi-stage rocket, when the first stage is ignited, when the first stage ignited, takes the satellite to some height, takes the satellite to some height, takes the satellite to some height, when the fuel is completely burnt up. When the fuel is completely burnt up. Okay, when the job of first stage, is over, it gets detached and is discarded. Immediately the second stage takes over. Immediately the second stage takes over the task, of producing further acceleration, okay? Acceleration. The second stage gets detached. The second stage gets detached, and the third stage takes over. Third stage takes over the further job, and so on, okay? The velocity of the rocket, thus goes on increasing at each stage, and finally horizontally thrust, and finally and finally a horizontal thrust, a horizontal thrust, puts the satellite in an orbit around the earth on reaching to a desired height, okay, to a desired height, okay. Theory, okay. Theory of rocket, okay. To derive the relation for the propulsion, let us suppose that rocket along with its fuel has a mass capital M, and is moving with velocity vector v at any instant, okay. Let this velocity be considered with respect to some inertial frame of reference, okay. Which is assumed to be the earth in this discussion. After a time delta t, let the mass of fuel ejected be delta m with an exhaust velocity ve with respect to the moving rocket. The velocity ve is the constant and being downwards related to the rocket is intrinsic negative quantity. The velocity of the object ejected cases with respect to the earth is given by v naught equal to v plus v0, okay. After some time, okay, delta t, let the mass of fuel ejected be delta m. Let the mass of fuel ejected be delta m with an exhaust velocity ve vector with respect to the moving rocket. With respect to the moving rocket, okay? Moving rocket. Moving rocket. The velocity v is constant, being downwards relative to the rocket, is an intrinsic negative quantity. The velocity of the ejected gases with respect to the earth is given by the velocity of the ejected gases. The velocity of the ejected gases. Ejected gases with respect to the earth, with respect to the earth, with respect to the earth is given by v naught vector equal to vector v plus vector ve, okay? As mass delta m has been fired out of the rocket, the mass of rocket decreases to m minus delta m, okay? After the exhaust and velocity increases to as mass delta m has been fired out of rocket, fired out of the rocket, okay? Of the rocket, fired out of the rocket, the mass of rocket decreases. The mass of rocket decreases to m minus delta m, after the exhaust and the velocity increases, to vector v plus delta vector v, where delta vector v is a small increase in velocity, okay? In the initial frame of earth, initial momentum of the rocket with fuel P, initial momentum of rocket, initial momentum of rocket with fuel, P1 vector equal to capital MV vector, okay? And final momentum of rocket and exhaust gases. Final momentum of rocket, and exhaust gases, P2 vector equal to m minus delta m vector b plus delta v plus delta m vector v plus exhaust velocity v, okay? So delta vector p equal to P2 minus P1 vector equal to vector m minus delta m vector v plus delta v plus delta m vector v plus ve vector minus mv. minus mv vector, okay, equal to capital M delta M delta M minus delta M delta V vector plus delta M VE vector are delta P vector equal to capital M delta V vector plus delta M VE vector, okay. I'm neglecting delta M delta V vector being the product of two very small quantities as delta M stands to 0 and delta V stands to 0. Dividing, this is the equation first, okay. This is the equation first. Dividing 1 by delta t and taking limits when delta t stands to 0. Dividing first by delta t and talking limits and taking limits when delta t stands to 0, we have dp vector upon dt equal to capital M dv vector upon dt plus dv vector upon dt plus VE d capital M by dt, okay. We have considered delta M the mass of the ejected gases. Delta M the mass of the where delta M is the mass of the ejected gases. Mass of the ejected gases as a positive quantity. Positive quantity but as the mass of the rocket decreases with time, but as the mass of the rocket decreases with time. The expression dm by dt is also d capital M by dt is also an intrinsic negative quantity, okay. Negative quantity for the rocket system. Okay. For the rocket system. So dp upon dt equal to capital M dv upon dt plus ve minus dm upon dt, okay? Capital M dv upon dt plus ve minus dm upon dt. Okay, according to Newton's second law of motion, as applied to the total system consisting of the rocket and ejected gases, dp vector upon dt equal to vector fe. According to Newton's second law. According to Newton's second law. According to Newton's second law, okay? A law of motion as applied to the total system considering the rocket and ejected gases, okay? Where Fe is the external force acting on the system. Where Fe is the external force acting on the system, okay? So Fe vector equal to capital M dv upon dt minus ve vector dm upon dt. So capital M dv vector upon dt equal to Fe vector plus ve vector d capital M upon dt, okay? Where capital M dv vector upon dt gives the net force, acting on the rocket, okay? Acting on the rocket. Thrust on the rocket, okay? If the thrust on the rocket, okay? If the rocket thrust on the rocket, okay? If the rocket is moving in a region outside, the influence of the gravitational pull of the earth and there is no air, and there is no air resistance or any other external force acting on the rocket, then F equal to 0. Okay. Hence force acting on the rocket is given by hence force acting on the rocket is given by force acting on the rocket is given by capital M dv vector upon dt equal to ve vector dm upon dt. This is the equation number 3rd. Okay. This is the equation number 3rd. The quantity ve, the quantity ve dm upon dt is the reactive force, is the reaction force, okay, exerted on the rocket by the exhaust of gases and gives the thrust, okay. Rocket thrust. In rocket thrust is equal to v vector dm upon dt, okay, as both v and dm upon dt are the intrinsic negative quantities is positive, as ve vector and dm upon dt as both intrinsic negative quantities, okay. But so this both is positive, okay. The thrust on the rocket is in upward direction, but ge dm upon dt vector dm upon dt is positive. The thrust on the rocket is that the thrust on the rocket is in upward direction, okay. Near the earth, the upward thrust on the rocket is opposed by the external force of gravitational mg, the weight of the rocket neglecting friction etc. Fe vector equal to mg vector, because near the earth the upward thrust on the rocket is opposed by the external force of gravitation, force of gravitation, mg vector equal to the weight of rocket, okay, the weight of rocket neglecting friction, etc, okay. Hence capital M dv vector upon dt equal to ve vector dm upon dt plus mg vector md is negative quantity as g acts in the downward direction and has a magnitude minus g in order to have a large thrust. Okay, a point A, the velocity of exhaust v should be large. The velocity of exhaust VE negative should be large. Okay, V point. T capital N upon dt, the rate at which the fuel is burnt and ejected should be large, and ejected should be large. Okay, ejected should be large. Equation of motion. Next is equation of motion. Okay, equation of motion. Okay, next is equation of motion. Okay, equation of motion. Okay, to get the equation of motion, of a rocket, which is motion of a rocket which is far away from the earth, we have rewriting equation third, d vector v equal to ve vector d capital M upon m. This is the equation number 5th. Okay, if m0 is the initial mass of the rocket and v0 is the initial velocity of the rocket and v vector v and m the instantaneous values of the velocity and the mass of the rocket respectively, then integrating equation 5th, we have v naught to v vector equal to ve vector m naught to m dm upon m. Okay, dm upon m. Okay, r vector v naught to v equal to ve vector log e capital M naught to m. Okay, r vector v minus v naught vector equal to ve vector log e capital M upon m naught. Okay, vector v equal to v naught vector plus ve vector log e m upon m naught. Okay, taking magnitude we get v equal to v naught minus ve log e capital M upon capital M naught. Okay, capital M upon capital M naught r V equal to V naught plus VE log E capital M naught upon capital M. Okay, this is the equation number 6. This is the equation number 6. I directed a V is opposite to the V. As directed at direction of VE is opposite to that of V. Okay, to that of V. Maximum burnt out velocity. Maximum burnt out velocity. Maximum velocity. If MF is the mass of the impulse, if MF is the mass of the rocket, impulse rocket at burnt out is that when the entire fuel has been exhausted and Vf vector is the maximum final velocity, is the maximum or final velocity, maximum or final velocity called burnt out velocity. Then from equation 6 we have Vf vector minus V naught vector equal to minus VE log E M naught upon MF. Okay, this is the equation number 7. Okay, this is the equation number 7. The negative sign indicates that the velocity imparted to the rocket Vf is in direction opposite to the velocity of the ejected gas. If the rocket starts from rest, V naught vector equal to 0, then Vf equal to minus VE. Vf equal to minus VE log E capital M naught upon MF, where Vf is the maximum or final velocity. Okay, the negative sign indicates that the velocity imparted to the rocket Vf is in the direction opposite to the velocity of the ejected gases. Okay, thank you. And next heading is collision.